quick review where we left off with some regression stuff. This was a ways back. We just want to make sure that we're all on the same page in terms of exactly what's going on when we are starting to partition things out and run these simultaneous regression models. Remember that first, what we've got here, when we're partitioning our sums of squares, this is very, very similar, functionally identical to what we're doing with our ANOVA models. Alicia, what is this sum of squares y? What are we getting here with the sum of squares y? Yeah, right? So here we're looking at deviations from the mean. Everybody's individual score, deviations from the mean. And what do we call some of the square deviations from the mean? Someone want to help her out? What day tomorrow? I saw you look at me. What are the sum of square deviations from the mean? What do we call that? We divide it by n minus 1. What's that?
I'm not sure.
Division between, you say?
Standard deviation or variance.
Variance, right? This is just the variance. This is variance that we've been calculating all semester, right? This is just total variability of y. This is just the sum of squared deviations from the mean, which is going to give our sum of squares of y. Individual scores subtracted from the mean. When we're doing group-based analyses, this is just sort of variability with our data. So nothing new or scarier. This is just total variability in our outcome, right? Then we've got our sum of squares regression. Chrissy, what's our sum of squares regression?
The difference of our mean from our regression line.
Yeah, difference in the mean from the regression line. Our sum of squares regression, this is the total, this is the getting the total predictive value of our regression line, right? Chris, if I have no variables in my model, right, that predict any variability in my outcome, what's my regression line look like? Flat, right? What's my best guess? If I have a regression model that tells me nothing about my outcome, what's my best guess every time, right? Just the mean, right? And so what our sum of squares regression is, it's looking at the sum of the squared deviations from the mean value to whatever predicted value on x given a certain y, right? So this is telling me how much better my regression model is than just predicting the mean, okay? And then last, we've got our sum of squares residual. Nick, can you tell me what sum of squares residual is?
That's our error term.
That's our error term. That's how far are we off. For every person, for every, in this case is a bivariate regression, for every x, we have a predicted value of y, an expected value outcome of y. Sometimes we're going to be very, very close. Sometimes we're going to be quite different. This residual piece of things, we're going to spend a lot of time in the next couple of weeks talking about these residuals. So wanting you to know what those residuals are, okay? Ignacio, what happens if I add up all these residuals?
0.
If they get to be 0, right? For my, with OLS regression, for the intercept and the coefficients that I've collected, there is no line that does a better job of minimizing the square residuals. There's nothing that I could draw through there that does a better job of minimizing those. Now we've got different estimators with different properties, but for OLS, with the things we usually do, this is the line that best minimizes some of the square deviations across each one of these, okay? And so this whole thing is very, very similar to our ANOVA models, right? Our outcome, our sum of squares y, this is just our total variability in our outcome that we're trying to address. My sum of squares regression, this is the difference in my group means from the grand mean, right? This is the grand mean, right? But if we had, think about this graph as not having a handful of spots. Think about this graph as having 10,000 spots on it, right? For every possible value of x, there's going to be, say, 100 different people for every value of x, right? My regression line, the expected value, for everybody who has a value of 2, it's the same. Right now, if I have 10,000 people in here, I'm going to have a whole bunch of people who are around at this point. But this is like my mean for 2, my mean for 2.5, my mean for 3, so on and so forth, right? So your sum squares regression is like your sum squares between. How far is my expected value, or the mean for this value of x, from sort of the grand mean, and then my residuals, this is how far each individual score is from the mean value. The mean value here being your point estimate on your regression plan, okay? So go through, take a look at this, make sure you've got an idea of how this fits together. This will be helpful as we start to sort of move on into other things, okay? So, and then our sum of squares are r squared. This is just our sum of squares regression. This is the variability we've accounted for over our total variability. Sum of squares of y. This is our r squared total variability accounted for by our model. Okay. All right. So we talked about significance testing. Talked about sort of what's going on there. We talked about multiple regression. Here we've got most basic form. We've got a couple of different variables. We've got b1 and b2. Relative to our bivariate regression, where we just have one, when we just have one predictor. Christian, how do I interpret for my bivariate regression? How do I interpret my regression coefficient? Okay, yeah. So, whoops. Oh, going the wrong way. Okay, so my bivariate regression, how do I interpret that coefficient there?
That is the amount that the outcome variable would shift with the independent variable.
Yep. So for every 1 unit of x1, I expect a 0.574 unit change in y. Is that always going to be 0.547? Nope. But that's what I expect. That's my predicted value, right? What is, Chris, will say with you, can you give me an interpretation of your standardized coefficient?
So when you transform those values, for every standard deviation, the outcome variable shifts 0.78 standard deviations.
Yes.
0.778.
Yep. So again, same interpretation here. Now we're just talking about standard deviation units. And literally all SPSS does is it just creates z-scores for your outcome and your predictors, and then just regresses the z-scores for your outcome on your predictors, and that's going to give you your standardized coefficient. So for every standard deviation unit and change in y, we get a 0.778 standard deviation increase in, or excuse me, for every standard deviation unit at change in x, we get a 0.778 standard deviation increase in y.
But that's different when you just transform one of them, potentially.
Yeah, and so we're not gonna, there are different forms of standardization where you would just standardize your x or your y, but we're not gonna worry about that. We're just gonna work on just your raw units, and then if you're standardizing the whole thing, okay? Siley, this standardized coefficient, if I'm talking about a bivariate regression model, what is that standardized coefficient equal? What is it the same as? So we got one predictor and one outcome. What is that standardized coefficient equal to?
0?
It's 0.778.
Yeah.
What is that the same as?
Repeat the question, please.
Yeah, so for a bivariate regression, right, what is this standardized coefficient equal to? What else, what does this look like? Chris?
It's a effect size.
It is an effect size. It is an effect size. What else is it?
Isn't it just your R value?
Yeah, and what do you mean, R value, what do you mean?
Like your correlation?
Yeah, it's just a correlation, right? This is just a correlation of x and y, right? The only thing that you get with a regression with only one predictor is you get an intercept, is you get a predictive equation, right? But your standardized effect in your bivariate regression, identical to your correlation coefficient. right? So if you ran correlation between x1 and y, your correlation would be 0.778. It's just a standardized effect there.
So the standardized slope of a line will be the correlation
In the bivariate case, when you've got one predictor and one outcome, changes when you got more, okay? And so here we have our R squared. This is the total proportion of variability in our outcome that's attributable to our set of predictors. Alicia, how many predictors do we have in this? One, right? So this is the total variability. How else could I get that if I was just running a correlation? If I looked at the correlation of x and y, what can I do that to get proportion of shared variability?
Is it partial A squared?
What's that?
Partial A squared?
Yeah, the R squared is similar to partial A squared. If I just have a correlation between x and y, and I want to know proportion of shared variability, what do I do that correlation? Square, right? So this is just a squared correlation between x and y, right? So again, your Pearson correlation, not any different than the stuff that you're getting from your bivariate regression. It's just that with your bivariate regression model, you get an standardized coefficient and then a predictive and an intercept there, right? So if you tell me that I have correlation between x and y is 0.778, what can I tell about that correlation?
It's pretty good.
It's pretty strong, right? But Ignacio, if I say, hey, I've got my x value is 5, what's my y value? And a corresponding y value going to be hard to do it with that, right? But if I run a regression model, I can say my expected value of y is 2.718 plus 0.574 x. Okay. Now if I tell you my x value is 5, can you tell me what my expected value of my outcome is? Well, you don't have to tell me, but yeah, you just plug 5 in there and then sort of go through and run it, right? And so this is where your regression model, remember that from a classic standpoint, regression is intended to be used to predict some outcome, right? And so here, this is nice, it tells us a magnitude and effect, really easy peasy. But what our regression model does is it gives us a predictive correlation. And then we can also grab a standardized coefficient. What's my standardized coefficient here? Yep, 0.778, right? Which is same thing there, right? Dead. You know how you keep throwing. All right. So, but then if I, in the bivariate case, and I wanted to get my R squared, if I take that, this turns into an R squared value, 2605, is that right? Yeah. Okay. So are people seeing how this all sort of fits together in the bivariate case? Okay. And then here are sum of squares. This is giving me my sum of squares regression. CJ, what is my sum of squares regression? What is it, Alicia? Prediction of the mean, right? So my sum of squares regression is going to be my sum of my squared deviations of my expected value, predicted value from the mean. Okay, that's my sum of squares residual. What is it?
Error.
Error. Well, what is it sort of literally?
I wanted to say error.
Okay.
No, it's your regression line from the individual values.
Exactly. The sum of squared deviations from my observed value versus my predicted value, and my sum of squares total. What's this, Ignacio?
Total is the total.
Total variability in my outcome, right? All is the total deviation of my outcomes from y, okay? And then tomorrow, my f value here. What is my f value telling me? I see that I have a very small p-value. What does that tell me? What is that a test of?
The F value?
Yeah, what is that testing?
Strength.
What's that?
Like the strength of the
Okay, cool, yeah. Strength of the regression, what is it specifically testing? What's the null hypothesis for that? Almost always when we have an inference test, it's testing whether or not something's zero.
Oh, yeah, so the F is testing, or I guess it's indicative of like how off from zero we are.
How what?
Like how far off from zero we are.
Okay, yeah. How far what is off from zero?
Our intercept.
Okay. Now, close. This one is a test of the intercept. What's my F testing?
The comparison of the predictability of our model versus just using the
Okay, cool. Yep, you're absolutely right. And so it's same lines as tomorrow. How much? So this is a test of, functionally, it's a test of the predictive quality of my model. Not a great one, but it's kind of getting there. What is this a test of? What are we testing is equal to zero based on this F?
Correlation.
What's up?
Your correlation.
My multiple correlation, my R squared. Basically, this is saying, is the model any good, right? This is a test, F is a test of whether or not R squared is equal to zero, right? And we have rho squared here, just because that's a population coefficient. So this animal model, in any regression that you get, this is just a test of whether or not my R squared value is different than zero, okay? So it is testing whether or not the model as a whole. So here we only have one predictor, so this is just basically functionally a test of the same, it's identical, right? But when we start getting into multiple regression, this is a test of whether or not my model as a whole is accounting for some non-zero proportion of variability in my outcome. Okay, yeah.
It's the same as your omnibus test that we've run before.
Exactly, it's the same thing as omnibus test before, right? Now the reason it's not a great indicator of strength is, let's say my model R squared, I'm accounting for 1% of the total variability in my outcome with my model, right? And I've got 100 people. Is that F likely going to meet traditional benchmarks? Probably not. What if I have 10,000 people in there? Yeah, it is, right? So again, like any other test we've talked about, all this is doing is saying, do we have evidence against the null hypothesis that some value is zero, right? But what we can do is we can go up and actually look at that R squared, and that has intuitive meaning, right? If I see an R squared of 0.01, that's pretty weak, right? If I have an R squared of 0.605, is that pretty impressive? Yeah, I've got a strong association between X and Y here, right? So as you're going through one, you just to be able to go through and put these together, sort of know where these values are coming from and kind of what each one of these things mean. Okay. Questions on this? All right. So here it is in this data. Talk about multiple regression. Now we've got a set of variables. So we've got predictor 1, 2, 3, so on and so forth in our most basic form. And I think this is where we left off, right? About right here. Talking about, so here's my regression equation with two predictors. Y hat, this is still my expected value of Y. This is still my predicted value of my outcome. A, this is still my intercept, still my constant. But my first coefficient now is a partial coefficient of the regression of X on B1 holding B2 constant, okay? And B2, this is the partial coefficient for the regression of X on B2 holding B1 constant, okay? And so someone tell me, if I'm holding it constant, what does that mean? Or controlling for, what does that mean?
You're incorporating the variability attributed to that variable in your model.
Okay, so I'm incorporating sort of the other stuff, right?
So it's I guess the unique contribution of that one variable.
Perfect. Beautiful. I'll give you a hug. Exactly right. The unique proportion of variability, right? So after we account for everything in B and X1 that's shared with X2, right? What's the unique association with Y after we section that out? Same thing with this, and this is why we call it a partial coefficient. Same thing when we're talking about partial eta squared, right? And when we're talking about a partial A squared is y after we control for everything else, after we pull that other piece out, right? Same concept. So our individual regression coefficients here are looking at, we're testing the unique association of my predictor on my outcome after we control for everything else in the model. Okay? So again, we talked about presenting partial coefficients. So when we're doing this, we're looking at a unique effect, right? So if I'm looking at the squared correlation of y on my outcome in x1, I'm accounting for, that's accounting for B and C right here, right? Because that's just the shared variability between x and y. If I look at correlation of x2 with y, I'm getting C and D, because that's everything that's correlated there. Squared correlation of C and E, or excuse me, of 1 and 2, that's this piece right here, right? But if I look at the shared variability of y with x1 controlling for x2, now I'm just getting B here, right? Siley, what happened to C? Why does x1 not get credit for C, even though region C is shared with y? Because it's constant, we're holding it constant. Why are we holding it constant? Why does x1 not get credit for C? So look at x1 and y. C is part of that overlap, but if I'm controlling for x2, why don't I get C? Anybody help her out? CJ?
They both brought the tortilla chips.
They both brought the tortilla chips. Everybody
Yeah,
bought chips. Everybody bought chips. Everybody was boring and basic. Like, oh, ooh, you brought some chips. Cool, right? We don't care about the chips, right? Chips are good. Chips are at the party. We have chips, right? It's just x1 doesn't get credit for that because it's overlapping with C, right? Same thing if we're looking at the regression of y on x2 controlling for x1. We're just getting D, right? So C is the shared variability. C is shared overlap between x1 and x2, right? And both of those, all regions B, C, and D all get counted into what statistic in our model? What do you think, Chris?
So Y.
Y.
No, hold on. So B, C, and D.
Yeah.
Calculating all of them. They're all the
R squared, yeah. So my R squared accounts for B, C, and D, right? Because I've gone through, and it's all variability that I've accounted for with my regression model, right? But my individual predictors, no individual predictor gets credit for C, because C is shared, okay? Now, tomorrow, if I have predictors that are completely uncorrelated with one another, is there any C? No, right? Because everything's separate, right? But do we ever have predictors in a set of predictors in psychological science where they're completely orthogonal to one another? No, not unless I have some sort of experimental manipulation that I'm working with, right? And so this is where we start to go through and with multiple regression, have to start accounting for not only the relation of X and Y, but the relationship among the X's with one another, okay? So I've got a situation at some point where I see X1 is very highly correlated with my outcome, and X2 is highly correlated with my outcome, but in my regression model, my test of my coefficients for X1 and X2 are both very much not different than 0. What's happened there? I have a significant model, right? My F value is quite large, right? But none of my predictors are reaching evidence for statistical significance. What's going on there? Chris?
Could it be driven by sample size?
What's that?
Could it be driven by sample size?
Not a sample size issue. Tomorrow?
Since they have, like, they're highly correlated, they probably have shared variance. That's not.
Yeah. If I start to put in redundant predictors in my model, what I can essentially do, I can have a situation where my model is predicting variability in my outcome, and my bivariate correlations between my predictors and my outcome are quite large. But in the context of my regression model, I have no significant predictors because they're all overlapped. I have a collinearity issue right there, and then there's other stuff that goes on with this. Okay. So are people seeing within the context of multiple regression how this stuff starts to fit together? Okay. So if I'm looking at my formula again here, my standardized coefficient for the regression of y onto x1 holding x2 constant is just going to be the correlation of y1 or y and x1 minus the correlation of y x2 and the correlation of x1 and x2 over 1 minus the squared correlation of x1 and x2. Same thing with b. My standardized coefficient for x2 is going to be the correlation of y and x2 minus the correlation of y and x1 multiplied by the correlation of x1 and x2 over 1 minus the square of the correlation of x1 and x2. My unstandardized coefficient is just going to be my standardized coefficient multiplied by the standard deviation of y over standard deviation of x, and then my r squared here. Okay. Now this is just for the 2 predictor case. Things start to get changed if we get 3, 4 predictors, but this is just kind of seeing where some of these coefficients are coming from. Okay. So my coefficient, my unstandardized coefficient, we're interpreting this as the expected change in y given the unit change in x, holding all of the predictors constant at 0, right? And my unstandardized coefficient interpreted the expected change in standard deviation units of y given standard deviation change in x, holding everything else constant at 0. This idea of holding everything constant at 0 just means we're sort of portioning things out. So just keep that as a framework for interpreting these, because it's going to be helpful as we start getting into moderation and stuff. So my significance testing or my inference tests for multiple regression, my degrees of freedom regression. Here in my ANOVA table, this is just the number of predictors. Degrees of freedom residual, this is just going to be my sample size minus the number of predictors minus 1. Degrees of freedom total, this is just going to be n minus the total number of people in my sample minus 1. Here's formula for standard, in the 2 predictor case, my standard error for my coefficient for B1, so we do the same thing for B2. So if we go up through and we take a look, Siley, can you interpret my r squared value here?
The correlated?
What's that?
The correlated?
Okay. Yep. And so how do we interpret an r squared value in our regression? What our r squared tell us?
Isn't it like eta squared?
Mm-hmm.
So it's like our effect size? Or?
It is an effect size, yep. And so what is it literally telling us here? What is it? How would you interpret that number?
That there is an effect? Or?
Okay, there is an effect. Can someone help her kind of take it to the next? So how would we interpret that?
That our variable x accounts for that percentage of the portion variability in our outcome.
Okay, close. So Nick's saying that our variable x accounts for this portion of variability in outcome. Tomorrow, how do we tweak that to make it just right?
It's our shared variability between our predictors and our outcome.
Okay, yeah. So want to be careful with shared variability, but this is just the total variability in our outcome that's being accounted for by our set of predictors, right? So in this case, we don't have just one predictor, we have 2 predictors, right? So 0.617, so we've got about 62% of the total variability in our outcome in these data that are being accounted for by our set of predictors x1 and x2. So this r squared value, this is a combination of unique variance and shared variance among those 2. It's just all the overlap. It's all the regions going on right there. Okay. Chrissy, what is my f value here? What is that? What am I testing here?
If the or if r squared is going to be 0.
This is my inference test of whether or not my R-squared value is equal to 0, okay? So here we've got a very, very small p-value. We don't have many people, but we've got a very large R. Again, we interpret this the same way as we have interpreted these things throughout this whole first year. This is just strength of evidence against the null hypothesis. And here we have very strong evidence against the null hypothesis of R squared being 0, right? Now that doesn't necessarily mean R squared is very large. Here, because we have a small sample, it does, right? But again, one, go through and be careful here. So regression, this is still some of the squared deviations from predicted value from my outcome. Now, it's not from 1x, it's the predicted value of any set of x's from means, right? It starts to get more complicated when we get into three-dimensional space, so don't worry about that. But this is still my predicted value, this is still my residual, this is still my total variability in my outcome, okay? Here are my coefficients. Ignacio, can you give me a interpretation of my regression constant here?
The constant?
Yeah.
This is just the intercept.
Just the intercept, what does that mean?
That means that if it's inside of the active range, it will cross the y axis on 3.09, 3.019.
Okay. Can you streamline that and give it to me? What is that? What is that 3.019?
Where it cuts the line.
Okay. You give me geometric answers. Mathematically, what does this mean? This is my expected value of my outcome when
everything is 0.
When everything is 0. Perfect, right? And this is where, with these regression models, right? If you have an aversion to math and equations, move past that, right? Because this will start to make a lot more sense. We're saying, literally, the expected value of my y is equal to 3.019 plus V1 times, whoops, plus 0.561 x1 minus 0.011 x2, okay? And if we look at that equation, right, now all of a sudden it starts to become very clear what my intercept is, right? This is just my expected value of my outcome when x1 is at 0 and x2 is at 0, right? Because of, as Nick pointed out last week, math, right? You plug zeros into those disappear, we're just left with that, right? So it's just the expected value of my outcome when everything else, when all my values are at 0, okay? Chris, give me an interpretation of this coefficient here.
When you increase your x value, your x sub 1 value by 1, you will increase y hat by 0.5, whatever, relative to the intercept value. Holding x sub 2 constant.
Right, okay. So we're saying if we hold x2 constant, right? If we hold x2 constant, we expect for every 1 unit increase in x, we expect a 0.561 unit increase in y. Okay. And then same thing here, x2, we're saying holding x1 constant at 0, but it can technically be holding x1 constant at anything at this juncture. But holding, controlling for x1, we're expecting every 1 unit increase in x2 to result in what, Alicia? Right, a negative 0.01, or a 0.01 decrease in my outcome, okay? So again, working through this and my standardized coefficients, again, we're just saying a standard deviation unit increase in x is expected to correspond to a 0.67 standard deviation unit increase in y, holding everything else constant. Here, a standard deviation increase in x should result in about a 1/10 of a standard deviation decrease in y, holding everything else constant. And then here, just my inference tests for whether or not my constant is 0, x1 is 0, and x2 is your coefficient for x2 0 in the population. Okay. So Sally, do we have strong evidence So what in terms of looking at these p-values, where do we have, looks to be fairly convincing evidence against the null hypotheses?
In the first x-intercept, it seemed like it, but in the second one, it doesn't seem convincing.
Okay, so my intercept is, right, that just tells me is my intercept equal to 0. Are we often interested in care if my intercept is equal to 0? Probably not, right? But fair enough, this is just giving me a test. And it looks like my coefficient, my unstandardized coefficient for x1, note that these are tests of not my standardized coefficient or my unstandardized coefficient, that my unstandardized coefficient for x1 is probably different. I have strong evidence that that's not 0, right? What about x2? What do you think, Sally? No, right? And so does that mean that the coefficient, the unique effect of x2 on y in the population is 0?
Can you repeat the question?
Yeah. So I've got a p-value of 0.30. Does that, or 0.43? Does that mean that the population value for the unique effect of xy or x2 on y controlling for x1, that population value is 0? Is that what that means?
Yes or no?
What does it mean, CJ?
It just means it's not 0. Wait, what was the question again?
So we have 0.43, right?
Sure,
Can I interpret that as evidence that the population coefficient for x2 on y holding y1 constant, that population coefficient is 0?
No.
No. How can I interpret that?
We just can't prove that it's not 0.
Yeah, it's just inconclusive, right? I have inconclusive evidence, right? And we need to be very important. Let's not forget all the stuff that we talked about last semester, right? And saying, oh, the effect is 0 or there's no effect. I can't say that. I just say, if you ask me what the unique effect of x2 is on y controlling for x1, I'm like, I don't know. I mean, here it looks to be pretty small, but again, also I don't know what the scaling on that is. It's kind of hard with our unstandardized coefficients to determine magnitude because it depends completely on the scale, right? And so this can start to become hard within the context of regression models. Before, when we're talking about mean differences, that's a pretty easy thing to think about in terms of practical implications. A little bit harder with regression models because we have to think about sort of what does a unit increase mean, right? If a unit increase is number of children on my net worth, is a 1 unit increase a big deal? Yeah, it's a pretty big deal. If I have 1 kid versus 2 kids we're getting big jumps, right? If I'm looking at a 1 unit increase in my income on overall happiness or something like that, and income is measured in dollars. Is a dollar a huge issue in terms of my yearly salary? Probably not for the people who would be like looking at this stuff right, instead of the US, right? And so thinking about what that 1 unit change means relative to what our outcome is and thinking about this stuff, okay? So one last thing before we want to go through and start taking a look, move on to the next stuff. So I have, tomorrow, if I'm looking at x2, in the context of my regression model, right? It looks like my regression model is quite good, right? That's a big R squared. So my model as a whole is accounting for a pretty impressive proportion of variability in sort of whatever it is that I'm predicting. Is based on my results, is x2 a big factor in that model?
Probably not.
It's not looking like it, right? That's a super tiny number, but I don't know, that could be something massive. It kind of depends on the scaling. But if I look at my standardized coefficient, you think about standardized coefficients run between -1 and 1-ish. You can have standardized coefficients that exceed 1 by a little bit. It's sort of an odd situation, but they can, right? For a standardized effect, 0.11 is pretty small, right? So it's looking like x2 in this horse race isn't much of a factor, right? But if we go down through here and take a look at our correlations, right? Alicia, what am I seeing as the correlation between X2 and Y? Y and X2? Negative 0.229, okay? So I've got a correlation that, I mean, to my hypothesis test gives me a larger p-value because I've only got 24 people in my sample, right? But if I have a sample of, I don't know, that's anything reasonable, is a correlation of 0.23, is that notable? Yeah, right? If we think about, remember our benchmarks for, think about R's and effect size, right? Anybody remember what benchmark for a small effect in terms of correlation is based on Cohen's standard? What is it? 0.3. 0.3 is a medium effect. What's a small effect? 0.1, right? And so we've got something that's somewhere in that small to medium effect in the bivariate case. When we go up to my regression model, that's now, it's no longer a factor in my model. What happened? Why am I getting evidence, at least some evidence of an association down here, but then all of a sudden my regression model goes away?
There's probably some similar variability among your two predictors.
Yeah.
Which sense one is stronger and it washes out the other one.
Yeah. So I've got correlation between X1 and X2 is 0.156. So it's not super highly correlated, but it looks like whatever in X2 was associated with Y, it's already been accounted for by X2 or X1, and so X1 just kind of sucked everything up and then left it for dead. Right?
So is this one, or I guess this might be depending on what type of regression that you're running, when the order of...
Yeah, hold on to that. We're talking about that's a stepwise regression, and that's a problematic situation. Yeah.
So that's what happened in this case. So X2 and X1 were switched. This would be different. Not this one.
No, not with this type of regression. This is a simultaneous regression where everything gets entered in simultaneously, right? Stepwise regression is a little bit different. Hold on to that. We'll get to that towards the end. Okay. But this is the reason, right? For if we're clinical folks, right? And I'm wanting to test out some subtle stuff. And I'm like, oh, I'm going to control for depression. I'm going to control for BDI. Is that going to work out for me? What's probably going to happen?
You're controlling both of those.
What's up?
If you're controlling both of those.
Yeah, I'm looking at some outcome and then I control for BDI. What happens a lot of the time if I'm looking at some sort of clinical thing? What's that? Yeah, I'm going to have a lot of overlap. BDI is probably going to swamp out anything. If anything that I'm looking at has anything to do with negative affect, BDI is just going, because it's a giant ball of just negative affect, right? It's going to suck out everything. Then I'm left with nothing, right? The relation of my construct with the outcome also has a massive overlap with just feeling terrible. And so then if I throw feeling terrible into the model, now everything that overlaps with feeling terrible gets sucked out and then there's nothing left over, right? If I'm an experimental person, I run a control for self-esteem, right? Is that a good idea? Christ, no, right? See, self-esteem is related to everything, right? And it's just, again, one of those constructs that's just going to suck out all the variability. Now, I mean, you can make an argument, does this predict something above and beyond? Even if I suck out to this major general factor, is it still going to predict? Then maybe you have an argument, right? But you want to be very, very careful. Same thing, I'm like, oh, I'm going to control for neuroticism. Well, if I'm looking like handicapping or something, self-handicapping, I'm going to control for neuroticism. Well, neuroticism is just a big general fuzzy mess, right? And it's going to go through and probably that thing that used to look pretty good. If I'm going to throw in something that's a general factor that grabs everything up, I'm going to be left with not much, right? So we have to be careful in how we're doing this.
Question.
Yeah.
It's always consistent that the correlation is not statistically significant and the t-value is also not statistically significant, or sometimes one is significant and the other not.
Yeah, that gets into, so we'll get into that sort of down the road. We get something, suppression effects that can happen,
Yes.
where you have a correlation. So if we're thinking about this, so I've got a situation where I have a correlation between X and Y. And then if I look at, say, my standardized coefficient, that's a kind of representation, standardized association between X and Y. What should, in the multivariate case, when I have a multiple regression, what should be the relation of my correlation to my standardized coefficient? The correlation, squared correlation, or the correlation represents total variability in my out-shared variability, and this is partial variability. What should your standardized coefficient look like relative to your correlation, bivariate correlation?
It should be positively correlated.
Okay, so there's going to be, yeah, maybe a relationship there, but is it going to be bigger or smaller? It's going to be smaller, right? Because my partial coefficient, anything that's left, anything that's shared with my other predictors, that's going to get, it doesn't get credit for that anymore, right? So what we start to see as I start to add more things in, oftentimes that standardized coefficient starts to get smaller and smaller and smaller and smaller as I start to add more things in, because there's more overlap and it gets less of a unique piece. But sometimes what happens, depending on sort of the situation, we can have something, a bivariate correlation that's very close to 0, and a regression coefficient that's very large, which suggests some sort of suppression effect, which is weird. We're not going to spend a whole lot of time talking on it about it, but we'll sort of do some work with that type of stuff. Okay. All right. So your standard errors for individual predictors here for X1 and X2 is going to depend on a couple of different things. One, how well your total set of predictors account for variability in your outcome. Okay. The larger my squared multiple correlation, or my R squared, is, the smaller the individual standard error. Okay. Why? So as my R squared increases, my standard errors for my individual predictors starts to decrease. Why is that?
Because your regression model is becoming a better predictor, right?
Yeah, I'm accounting for, like this error term, right? My sum of squares residual, this is the stuff that I'm not accounting for, right? And as my R squared gets bigger and bigger and bigger, this residual that we're using as to calculate standard error starts to get smaller. I'm just doing a better job of accounting for my stuff, right? So as my model gets better, systematically everything else held constant is going to start to reduce the standard errors for my individual tests. And Chris, see, if the standard error for my individual test decreases, what does that do to the power of my test? It increases it, right? If my standard errors are getting smaller, for these, again, remember that my t-test is just my unstandardized coefficient divided by my standard error. My standard errors are getting smaller. It makes my test more powerful, right? And so when we're thinking about powering, this is something we do in psychological science all the time, or at least in clinical, right? I have got my hands on some existing stuff, right? I want to put this thing together, right? And my total model is accounting for 5% of the variability in my outcome. What's that doing? What should I be expecting that to be doing to my standard error and the power of my tests? Makes them super weak, right? Because my model isn't accounting for much. Basically, all that variability in Y is stuff that I'm not accounting for, so it's all error, and that's going to make my standard errors for my individual predictors quite large, right? So thinking about putting together regression models that are well powered, it behooves me to try and think about, what am I doing? What is my outcome? What are the things that should account for my outcome? And sort of trying to put together a well-specified model as opposed to just, here's the two things I have on hand, okay? It gets a little more complicated on that. We'll talk about that down the road, but my standard errors are going to depend on my R squared value. But then also, these standards, or my standard errors, are also going to be determined by the extent to which my predictor is redundant with other predictors in the model. This is related to tolerance. We'll talk about that in a moment. But essentially, if I have huge overlap across my predictors, what ends up happening is I end up with very, very large and unstable standard errors. They start to jump around from one sample to the next, right? They're very, very variable. They're very, very large. And so I might have a standardized coefficient that's 0.76 with 100 people in my sample, but my hypothesis test, my inference test says that that coefficient isn't doesn't reach threshold for statistical significance, right? Probably suggests there's some sort of massive collinearity in my model that's a problem. Okay. Questions on that? All right. So, this is what we look like in SPSS. Stata, same thing, just kind of set up. Here's my R squared. Here's my x1, x2 constants at the bottom here, correlation coefficient. So regression is pretty easy to run here. Just reg y1, x1, x2. If you toss beta on the back, it gives you the standardized coefficients. If you leave beta off, it gives you confidence intervals. Pretty quick and easy. All right. So we're thinking about relative contributions within multiple regression. Okay. So in our simple regression, right, or if we have regression with a set of uncorrelated x's, right, my standardized coefficient or my just simple correlation is going to be a reasonable estimate of the relative contribution of my individual predictors. Okay, but as soon as I start having correlated independent variables, right, I have to consider the relation with correlation of my relation of my predictors with my outcome, relation of predictors with themselves, and unique relations with our sort of outcome to try and what we're trying to do is we're trying to capture some measure of effect size. Okay? So if we go through and we're thinking about different measures of effect, I've got my squared correlation of my y with my whatever my predictor is. This is just the proportion of shared variability variability in y that's shared with my x1. Okay, so if I take a squared correlation of x1 and y, I'm going to get that's going to be AB, because that's the proportion shared over ABCD, all the variability in y. Okay. So again, any Pearson correlation that I calculate, I can just square it, and it's shared variability between those two variables. Okay. Follow me here, see where that's come from on the diagram? Okay. But what I can also do is I can calculate within the context of multiple regression a coefficient I'm going to call a semi-partial correlation. Okay. Squared semi-partial correlation is the proportion of variability in y, the proportion of total variability in y that's unique to x. Okay. And in this case, in this diagram, my squared semi-partial correlation is going to be reflected through area A over A plus B plus C plus D. Why does this make some sense? Yeah,
You're accounting for all of the variance.
Yep. So I'm looking at the proportion of total variance, total piece of the pie. Why is in my squared semi-partial am I only getting credit for region A?
Because that's the only one shared with your outcome variable y.
So it's not the only one that's shared with it. What about B?
It's the only one that is uniquely
That's
shared.
unique to X1, right? B is there, B is overlapping. B got caught in my squared correlation, right? But my squared semi-partial, X1 didn't get credit for A, or didn't get credit for B because it's also squared with Y. Okay? So people seeing the difference between squared correlation and squared semi-partial correlation. Okay? So my squared semi-partial correlation is the total of variability in the proportion of total variability in y that's unique to x. Then we also have a partial correlation. A squared partial correlation is going to give me the proportion of residual variance that's unique to x controlling for other predictors. Okay, you can actually dispense with the unique piece. We can say proportion of residual variance attributable x controlling for other predictors here. Okay, and so if I square my partial correlation is going to be region A over region A plus D. Someone explain this to me. Yeah.
So you have the variable uniquely shared with x and your outcome y, and then the other variability that's unique just only to y.
Okay, yeah. What does this squared partial correlation sound like from last semester?
Partial eta squared?
Partial eta squared, right? This is just a partial eta squared. It's the same. It's functionally the same thing. ANOVA is just a special case of regression. There's nothing unique going on there except for the way we're talking about this stuff, right? And so what we've got is my my squared partial correlation is going to be the residual variance in y that's attributable to my x after controlling for everything else in the model, right? So after I take everything else that's accounted for all my other variables, pull that out, of what's left, how much of that is attributable to my x value, okay? So we've got three different possible ways we could start to conceptualize this relation. R squared is just a bivariate relation. X and y, how much is shared between those. We've got my squared semi-partial correlation. This is saying of the total variability in y, what's unique to x, right? And then my squared partial correlation, this is saying of what's left over after I section out everything that's accounted for by other predictors, what proportion, how much variability is left over in x with the residual variability in y. Okay? So my squared semi-partial correlation, this is a nice intuitive measure, right? Because I can say, of the total variability outcome, what proportion of that total variability in my outcome is unique to x1 in this set of predictors, right? That's an easy way to go through and think about things. My partial correlation, that's a little bit different. It's harder to think about, okay, so after I section out everything else that's overlapped with other variables, what's the residual variability in y that's left that's shared with x, right? So residual variability is kind of a hard thing to think about. The amount of residual variability of the pie that's left over really depends on what else was in the model. It could be a lot, it could be a little, but our partial correlation is important for the calculation of power in our regression models. And so, and this is also a nice benchmark. We don't have standardized benchmarks for partial eta or semi-partial, squared semi-partial correlations. We do have benchmarks for partial eta squared, or excuse me, for my partial correlation that I can use as an indexed measure of effect that starts to communicate things. Okay. So people starting to sort of see, so want to take a look when you're trying to piece this apart, looking what's in the numerator, what's in the denominator, and making your interpretation, trying to pull this stuff together. All right. And so again, my formula for my semi-partial correlation is identical to my standardized. It's a little bit different there. So essentially, knowing that my standardized coefficient can exceed 1 or -1, what you'll see sometimes is people will say, we'll take your standardized coefficient and square that and interpret that as unique variability in my outcome. Don't do that. That's not appropriate. If you want to do that, you should be looking at a squared semi-partial correlation, or if you're looking at residual variance, a squared partial correlation. Okay. But your partial correlation and your standardized effect will be very, very similar, to the point where I try not to report them in the same table because it seems redundant. They're very close, but they're not the same. So, other thing we could talk about here is an adjusted R squared, okay? So again, if we're thinking about the squared multiple correlation, your R squared, this is a biased estimate of the population parameter, okay? Based on what we talked about, if we think about R squared is the same as eta squared, why might we have concerns that R squared is going to be a positively biased estimate of the population coefficient? So I'm saying, here's R squared, right? And R squared, any of our statistics are intended to represent some population parameter. Why might I be concerned about systematic bias in R squared as a representation of the population coefficient? What do you think is going on here?
Because it's divided by n not n minus 1.
What's that?
Because we're, like, the denominator is n not n minus 1.
Okay. If we're talking about variance, right, that can start to be a little bit, that can start to go run any regression model with actual data. Am I going to get an R squared that's exactly 0? Can R squared be negative? So what's R squared always got to be? Some positive value, right? So even in the situation where my population coefficient is 0, I'm coming up with some theoretical situation where this set of predictors, this set of variables really shares 0 variability with my outcome. If I run a replication of 100 studies again and again and again and again and again, what's my aggregate R squared value going to be? Is it ever going to be 0? It's always going to be something, right? So same issue that we ran into with eta squared, right? So R squared is always going to be positively biased, right? And because it can't take negative, it can't be negative, right? It can't be ever, oh, it's predicting negative variance. It's always got to be, at the minimum, it's always going to be 0. If you carry that 0 out far enough, it's not going to be 0, right? So we worry about R squared being an overestimate of the population parameter, particularly when we're working with small samples, right? So my R squared of 0.617 in a sample at 24, and I'm worried at it, am I confident that that's a precise estimate of my population value? No, that's problematic. It's it's too big, right? So what we can do is we can go through and we can calculate an adjusted R squared. And what this adjusted R squared is going to do is it's going to calculate, incorporate some correction for some biases here. It's going to depend on my calculation of R squared. It's going to depend on my number of predictors, my sample size, and the larger ratio of my number of predictors to my sample size, the more penalty I'm going to get. So if I have a sample of 30, right, and I've got 2 predictors, I'm probably going to get a decent penalty for comparing my R squared to my adjusted R squared. But if I have 10 predictors and 30 people, I'm going to get a much bigger adjustment in terms of my penalty here. Okay. So once again, just like when we were talking about omega squared and eta squared. Omega squared, still a positive biased estimator of population coefficient and ANOVA, but it's better than eta squared. Same thing, adjusted R squared is not unbiased, but it's just going to be a better estimator than R squared. Now, in some fields, some people get really worked up about this adjusted R squared. We don't tend to worry about it too much in psychological science. Ignacio, in marketing research, do you?
R squared.
What's that?
Most of the time,
Yeah.
you take care of the R squared because it's easier to interpret. It's kind of more
Okay, so people don't worry
universal.
too much about adjusted.
Yeah.
You'll see some fields where they will, if you try to report an R squared, you get in big trouble with that. One of the reasons we don't worry about it too much in psychological science, are we ever trying to, is the purpose of our studies ever to maximize the total amount of variability on outcome we're accounting for? That's rarely the case, right? Now, if I have some practical outcome, if I'm, say, working in, say, insurance, if I'm an actuary, right, and I'm trying to get the best predictive model as I possibly can for some sort of functional outcome that has real-life implications, maybe then I'm trying to put together a model that maximizes that R squared. What we do in psychological science is rarely that. We're usually interested in testing unique effects and things along those lines, so we don't worry about it a whole lot. But know that if I'm working with models with very small samples, which you shouldn't be if you're using regression, but if you are, so that's what that R squared value is for, or that adjusted R squared is for. So in SPSS, this is an expanded output. So what we're doing in SPSS is we're getting semi-partial correlations in SPSS are identified as part correlations. Partial correlations are identified as partial. And what we can do is we'll go down and show you how to go through and request this from your output. If we go through here, we see our R squared. Now here we've got a sample of 24 with 2 predictors, and the difference between my R squared and my adjusted R squared, 0.67, 0.58. Right? I accrued a pretty big penalty for that, right? Now, I didn't have a ton of predictors, but I only have 24 people in my sample, and so now you got a pretty big downward shift from my R-squared to my adjusted R-squared because my sample was really small. Like, you should never be running a regression in a sample of 24. I did for this, but just kind of see what's going on, okay? Other thing too, when we ask for part and partial correlations in SPSS, it's going to tack on this little piece here to my regression table, and this is going to be my zero order correlations. What are my zero order correlations? What do you think, Nick? Yeah, Chris?
Is it your unpartial correlations? Like it's just your straight up correlation?
Yep, this is my Pearson correlation. My zero order correlations, these are just my Pearson correlations. This is just bivariate correlations that we would look at or calculate in a regression table or a correlation table. So zero order, these are just my straight up correlations, my Pearson correlations. Partial, this is my partial correlation, my PR. Part is my semi-partial correlation. Okay. So if I'm looking at sort of this outcome, so we'll generally see my standardized coefficient be smaller than my zero order correlation, but larger than my semi-partial correlation. Okay, and the relation between my standardized effect or my standardized coefficient and my partial correlation will go back and forth, but they're generally going to be fairly similar. Yeah, 0.761, 0.77, maybe 0.17. These are really tiny effects here. But what I've done here is I've gone through and I've taken my semi-partial correlation and squared that. Someone be brave. Tell me, make an interpretation of that squared semi-partial correlation for X1. Go for it, Chris. You're a brave man. I can see it. I can see it in your eyes. You're crazy, man. This guy's a lunatic. He's going to just do it. What is it?
Is the proportion of variability unique to X1?
Yeah, right. The only thing I would tweak with that, you're exactly right, right? The only thing that I would tweak there is I would say it's the proportion of total variability in Y that's unique to X1 within this model, right? And why did I specify total variability in Y?
Because we're talking about
The whole piece of the pie. Because I can take that partial correlation and I can square that too. And that's going to be, if I square the partial correlation, that's going to give me the proportion of residual variability in Y that's attributable to X, right? And residual variability, that means after I sort of take out everything that's due to the rest of the model, whatever is left over, this is the proportion of that, what's left over is that's unique to Y, right? So when we're thinking about squared semi-partial correlations, talking about this as the proportion of total variability in Y that's unique to X. If I'm talking about squared partial correlations, I'm talking about the proportion of residual variability in Y that's attributable to X. You don't really have to say unique when you're talking about partial correlations because there's nothing else. If there was anything that was shared with anything else, it got sucked out anyway. So you're just talking about what's shared with X that's left over after we suck everything else out. Okay. And so this will be important sort of to start to understand and making sure you're solid on those Venn diagrams. Question here. All right. In Stata, Alicia, so again, regress ag Y, X1, X2, it's easy, right? Here's your adjusted R squared, easy peasy. For you to get your, for your partial and semi-partial correlations, you just take that statement and delete reg and put p core, and then it just gives you everything. What's nice here is you get your partial correlation, your semi-partial correlation, and then it squares your partial, it squares your semi-partial, all that for you already, so you already have that there. All right, cool. Questions up to sort of how we're going through and thinking about regression and teasing things apart up to this point. Okay. So up to this point, we've been talking about ordinary least squares as our estimator, okay? But ordinary least squares isn't the only estimator we have available to us. There are other things, other ways we can go through and start to estimate our regression models. And what we want to do is choose an estimator that has certain properties that are desirable, okay? And when you start to get into methods literature and start looking into things, you'll start hearing people start talking about these in terms of characteristics of estimators and standard errors and things along these lines. If we hear someone talking about unbiasedness of an estimator, okay? If an estimator is unbiased, we're saying that values of our sample parameter are expected to be equal to the population parameter, right? So we know, just like anything else, so we talked about unbiased, we haven't called it unbiasedness necessarily, but we've talked about it a lot. Is the mean an unbiased estimator of the population mean? Is the mean an unbiased estimator of the population mean? Sample mean. Yep. And why is it an unbiased estimator? Do I think if I collect a sample of height from the average height of a random sample of college students, that value is equal to the population parameter? Nope. But if I were to do that over and over and over and over and over again, the distribution of my sample means, I expect to be equal to the population mean, right? And so we would say that the mean is an unbiased estimator of the population mean. The sample mean is an unbiased estimator of the population mean. And now when I'm talking about regression estimators, if I have an unbiased estimate, it would mean that if I were to replicate my regression model an infinite number of times, the average of that coefficient would actually be equal to the true population coefficient, okay? If I have a biased estimator, it means that over an infinite number of replications, the average of my coefficients is going to be somehow bigger or smaller than the true population estimate. So then we would have a biased estimator, and then we would probably have problems with that. People see unbiased estimators. Okay. We also talk about the efficiency of estimators. Okay. Thinking about efficiency of an estimator as being the inverse of its variability. Okay. With estimators with smaller variance being associated with greater efficiency. So let's say that if I have I've got n equals 100, and I've got x1, x2, and x3. Okay, and I want to run and then some y. I want to run a regression model here, right? And I've got two different estimators, right? I've got estimator 1 and estimator 2. Okay. And let's say what I've gone through in some sort of simulation research or something like that, and I'm looking at the sampling distribution of B for my first one. I get this is a sampling distribution of B1, right? So over 1,000, let's say 1,000 replications, right? Is my coefficient for B1 here? Is my coefficient for B1 going to be the same in each one of those replications? No, it's going to be different, right? It's going to jump over. And so what I can get is a sampling distribution of that, right? Now let's say I go through and I do the same thing, same data, but I use estimator 2. So this is the OLS, let's say I use something else, right? And I find that under this other estimator, this is my sampling distribution, B1, okay? Which one of these do I have more, is there more variability? The second one, right? And so let's say for both of these, the average value is 0.25. Okay. And my actual population value so are either one of these estimators biased? not biased, right? But which one's more efficient? B1. B1's more efficient because the variability of my sampling distribution is lower, is less than this, right? So I'm expecting for B1, I've got an efficient estimator here, in that I have more confidence that my coefficient for any individual study is going to be closer to the population effect than an estimator 2, right? So neither one are unbiased, but what I've got is one estimator that's more efficient than the other. And so my sampling variance of my OLS, this is why we use OLS so much. The OLS is an efficient estimator. If I've gone through and I haven't violated assumptions, OLS is a more efficient estimator than some of the other options that I can use. Not to say these other options are unbiased, it's just the sampling variability of the individual coefficients is going to be wider, bigger than what it is for OLS. So people comfortable with efficiency as sort of a concept? Okay. Last thing we're going to talk about is consistency. We say that an estimator is consistent if my estimated parameters start to get closer and closer and closer to that population parameter as my sample size increases. Okay. In general, Sally, am I thinking my estimators are going to be, what's going to happen to my estimator as my sample size gets bigger and bigger and bigger? If we're talking about a mean, right? Is my sample mean going to, what's going to be the relation of my sample mean to the population mean as my sample starts to get bigger and bigger and bigger?
It's going to be closer to the bottom.
It's going to get closer and closer. As my sample size increases, the mean as an estimator is going to get more and more accurate. It's going to get more precise, right? If I have an inconsistent estimator, I might have the same variability of the sampling distribution at 100 people as I would at 10,000 people, right? I don't have a consistent estimator. My consistent estimators are getting asymptotically close to the population parameter as my sample size starts to increase. Okay? So when we're thinking about estimators, these are properties that when we're choosing something, we want something to be unbiased, we want it to be efficient, and we want it to be consistent. And this is why, in general, we'll go through and typically using OLS. OLS is pretty robust and it tends to have pretty good properties in terms of the types of things we do, right? Now, certain types of analyses, certain types of data may start to pull for other types of estimators, right? So if I have collinear variables, right? If my predictors are all on top of one another, very, very, very highly correlated predictors. Ordinary least squares is still unbiased, so population effects are still close, and they're consistent. It gets closer and closer to the population estimate as things increase, but it's no longer efficient. When I start to get large and stable standard errors, and my coefficients start to jump around all over the place, and so it's no longer an efficient estimator, right? And so when you get into literature and it starts talking about properties of estimators or when I might want to use something different, what can happen is if I have data that starts to violate some sort of assumption or has some sort of known characteristic, I may want to go through and say, well, under this circumstance, ordinary least squares is no longer an efficient estimator, and so this is where we might switch into something else. Questions on sort of this? All right. Other estimators, so again, we will typically use ordinary least squares. Ordinary least squares probably the most common, but we have other functions, ordinary least squares, weighted least squares. Weighted least squares is something we use if we have heteroscedastic data. We'll talk about that. If I have non-constant variance in my residuals, that might be a reason to switch over and say, okay, I've got a violation that weighted least squares can do a nice job of addressing, right? Least absolute residuals. So these are all different ways of calculating your residuals. So again, with data that have extreme heteroscedasticity, we'll talk about what that is. Sometimes use a weighted least squares, but this is the thing that happens sometimes when people start to get sassy with their statistical knowledge, right? Sort of want to use weird-ass tests without having a good justification for it. If you're going to do something that's different than what people typically do, just have a good job for a good reason for doing it, right? Not just doing it to do it, right? Saying, you know, based on the characteristics of these data, what I decided to do is go to this because this is going to be an optimal estimator given the characteristics of these data, and sort of take things from there. Yeah. Questions? All right, cool. That takes us, we still got half an hour. All right, let's just jump into screening stuff. We'll move through this first piece quickly because you all read the chapter, you all know about a lot of this stuff. So, and a lot of this is going to be reviewed, so I'm going to click through it pretty quick. But if people have a question, so raise your hand, stop me, so I'm not screaming through stuff. Okay. Can we agree? Everybody look at me. Okay, good. I see that, right? Flying back, hey, stop. Dude, you fast. All right, cool. So what we're going to do, talk about general screening, overview stuff, then we'll get into the regression-specific assumptions, and then talk about screening, the difference between screening our observed variables, and once we get into residuals with our regression. Okay. Yeah, Ignacio.
So
That was quick. I didn't make it too much, but
just going back just a few steps. So you can use least squares to run the regression, right?
Mm-hmm.
But also the other two methods you mentioned.
But also
The two other methods.
yeah.
And you talk about heteroscedasticity, and you say you can use the second one
Mhm.
to get rid of that one.
Yeah.
But in SPSS, where is that option? You know, like.
You can probably specify a weighted least squares option in there somewhere. I would have to dig around for it. Generally, and we'll talk about this, heteroscedasticity generally doesn't degrade your solution too badly unless it's real severe. And then there are other ways of doing it too. So one of the reasons I like some of the benefits of switching over to Stata is you have an option for a robust standard error option that uses a kind of a different thing, right? So you can start to go through and address some of that.
So you just click somewhere, weighted least squares.
Yeah,
and you make
it'll go through and do that. But weighted least squares has its own problems, and generally I think you need pretty large samples in order to pull that off. And then that starts to become a problem. Okay. All right, so screening. Why worry about screening? We've talked about screening, but thinking about revisiting sort of why this is important. One, I decided to do some analyses, right? But this analyses, these aren't a free-for-all, right? These are analyses, and sort of proper inference from these analyses are predicated on something, right? There are certain criteria that need to be met. If I don't screen my data, I can't tell whether or not this is an appropriate analysis or what types of features of my data can start to screw with that, right? And so it starts to become important there. Maybe more important, it starts to give me a very, very good sense of what's going on in my data. For any defense, theses, dissertation that you all have with any of us, by the time you walk into that room, I should be able to ask you nothing about that data that you don't already know back to front, because you've had that data and been working that data forever. I don't. I can ask you sort of random questions like, well, actually I did that. This is what it looks like. Knowing what your data look like is going to give you insight into sort of how people were responding, and hopefully give you understanding about phenomena of interest and things along these lines. Yeah.
Is there like pizza available at the end of the defense process?
I don't know. You could bring it. I would suggest bringing the pizza before.
Okay.
As a subtle bribe or an overt bribe, however you want to do it. You just kind of throw it down, right?
Okay.
Or right, come in with like a pineapple pizza. It'd be like an act of aggression, right? It's like giving me the finger before you walk out, right? Don't do that. Because I'll get mad and tell you. But yeah. All right. Other thing. Thinking about what's next. Okay. I wouldn't do that. That would be good. Now I'm on.
You got it.
Except for Brian. Yeah, it says there already. Laura, we're going to talk about the editing of this film. This is the goes off. Right. So thinking about what's the next question. So I'm seeing things that are going on my screen that don't have anything to do with what I did, but there's interesting stuff going on that I might have developed hypotheses for, and say, hey, so we kind of missed this, but I wonder what's going on. Here's my idea. I wonder if we could go through and test that, right? So going through and spending time you will spend more time screening and sort of cleaning your data than you ever spend actually doing your analyses. That's just how the world works, but it's actually a good thing, right? One of the things you can start to do, and I think so this is a classic example, this quartet sort of given, so we've got 4 different sets of data. And these sets of data all have the same regression line, standard error, looking at the relation between x and y, right? So if I run a bivariate regression of x and y for each one of these, I'm going to get identical, the exact same results every single time, right? But if I look at the scatter plot of these two, very, very, very different things going on in each one of these data, right? Here, does regression look like it might be an okay thing to do here? Yeah, it looks fine. What about there? Nope, right? We've got a very, very clear nonlinear effect going on right here, right? And so if I just run this regression, if I regress y onto x1, and they're like, okay, here's the relation, I've missed something very important going on in these data, right? What about here? What's going on with this situation? CJ?
You got that outlier there?
Yeah, I've got a high, when we talk about this, I've got a high discrepancy, right? And what is this point doing in my regression line? It's changing it, right? It's shifting it up, because that regression model, this line, this association has to adjust for this guy that's hanging way up here, right? If I get rid of that, I've got a perfect correlation, right? But with that, it's going through and shifting the slope, making it look stronger than it is. If I would have screened that, I would have identified that very clearly as an issue, right? What about right here? Yeah, you've got another outlier, right? This one's just kind of happening way out here, right? If I get rid of that person, I've got a very different relationship. I've got one data point that's driving this whole regression line, right? But if I just go through and I just run my data, right? If I just tell SPSS to give me a regression, I've missed very important things going on. So it's a pain, and there's a lot to go through and wrangle, but very important. So even one, knowing whether or not you can rely on any inferences from your test is important, but then just understanding your data, the phenomena of interest, and sort of what's going on with stuff. All right. So, yep, all good things. So, first thing we're going to work about, accuracy and plausibility. We've been doing this all for the last semester. This is just going through, are my data within range? Has everything been coded properly? Are the labels correct? Do I have a different expected number of cases, right? Different things that can go on as I get things that are out of bounds, because we get RAs that enter, well, someone entered 10, and so I entered 10. Big, what's only at 8? 8's the top. No one can have a 10. Like, you can have an 8, no one gets a 10. And now all of a sudden I've got a value that doesn't make sense, right? Or someone miskeys something, or someone's entered a 999 code when 999 isn't, so you're out from, right? Are labels applied correctly? Done that before. So the 0's men, 1's women, flip the code around, now all of a sudden I got all these dudes in my set that doesn't make sense to me, because that's not how psychological science works, right? You have to go back through and flip that back around, right? So at least that's something that's catchable, right? But what if CJ's running an experimental study, has 3 different conditions and mislabels them all backwards, right? Now all of a sudden your study doesn't make so much sense, or you get super jazzed about some exciting new effect that you found that no one ever is going to replicate because it's not an effect, you just mislabeled everything, right? So always wanting to go through and make sure everything ties back into your hard copies, that everything is looking good, okay? So again, just pulling down, looking through descriptives, thinking along those lines, okay? Also want to be thinking about missing this. We haven't talked about this a great deal, but it starts to become important. Thinking about, and in that Tabachik Fidel chapter, they're talking about patterns of missing this, so the mechanism of missing this, right? If I have missing this that's random, true random, we often say that's ignorable, right? Assuming that there's not a ton of data I'm missing, but if it's just a few cases and they're missing data sporadically, just kind of at random, then those are ignorable, right? But if we have non-random missing this, now we have systematic issues that are going to start to impact my ability to generalize, and so the inferences that I'm drawing from these data. Okay, so Tabachik, they'll talk about this. There's a paper I'm going to have you read. I downloaded a handout, put that in the handouts folder. Make sure to take a look at that missing data worksheet there. but Ruben and Little have come up with a way of talking about missingness that starts to put things into 3 different categories. First category here is going to be missing completely at random, or MCAR. Okay, MCAR data, probability of the presence of or absence of a given value of y, independent of all of the values of y, or independent of all of the variables in the set, including y. Okay, so whether or not I have a value for my outcome is completely random. It's it is dependent on no thing. It is a true random event, right? It doesn't, the presence or absence of of a value there doesn't depend on any of my predictors, doesn't predict on the value of y, a truly random event. Okay? You like that?
Oh, I was thinking I was
a new ska band name, just random.
No, we're gonna stick with the one for a while.
Okay, good.
Till it runs out of steam.
Right. All right. So missing completely at random. This is something that we would say is a true random event. Okay. This is different than missing at random. Okay. If we have data that are missing at random, the probability of the presence or absence of a y value does depend on the observed value of x or some combination of x, but it's unrelated to the actual value of y after controlling for the predictors of the model. Okay. Basically what's going on is missingness is attributable to other variables in the model, right? I have missingness, but I know why it's missing, right? And it's if I have data that are missing at random, it doesn't mean that my data are actually truly missing at random, because that's MCAR. Missing at random says that my data are missing because of something that I've measured. So the mechanism of missingness, the reason that I'm missing values, is accountable for some values that I do have, so values of my x or something along those lines. And so once I account for that piece of things, everything else is just random, right? So I can have a situation where the likelihood of having or not having some value of my outcome is dependent on something, right? So let's say, Chris, you were running some eating pathology stuff, and sort of the likelihood of you having some outcome is directly dependent on someone's BMI, right? So as people's BMI increase their follow-up data or something like that, it starts to drop out because people are ashamed or something like that and don't want to come in. It's a weight loss thing. And so if I'm doing good and I'm low, and my BMI is low, then I come back in and fill out sort of whatever sort of psychological variable. But as we start to see that as people's BMI increase more and more and more towards the high end of the scale, we start to see people not coming back for follow-up. So our Y is missing based on higher BMI. Those data aren't missing completely at random. They're systematic missingness, but it's missing at random, because as long as I have people's BMI, I know why these last ones are missing. And so within the context of like an SEM or something like that, we would still call that ignorable missingness, because I know why those values are there, and so the variables that I do have in the model are accounting for that. Missing not at random, this is a probability of presence or absence of a given value of y is dependent on the true value of y and maybe other x's as well, right? So I might, in this situation, I'm having missingness that's due to sort of the actual value of my outcome, but I have no way to account for it, right? I might think, oh, what I'm thinking is people who tend to be heavier and who are high BMI are the people who aren't coming back, and now I'm missing those data. But if I don't have their actual BMI, I have no way to model that. And now that's non-ignorable missing. This is missing not at random. And if I start to analyze these data, when we get biased results, I'm going to have problems with generalization, because I don't have a method of going through and addressing this stuff. Okay. Tabachik and Fidel talk about this. Switzer and Roth missing data worksheet. Go through, take a look at that. They give a really, really excellent example of this. It's based on blood pressure and sort of heart stuff in this paper. Does a very nice job of helping tease some of this stuff out. Questions about missingness? Distributional assumptions. Again, when we're looking at data, wanting to screen things out, wanting to think about a couple different types of normality. Univariate normality, this is just scores given a normal distribution. Talked about that, no one's shaking on that anymore. Multivariate normality, this is a little bit different, right? This is where we started talking about, we had talked about bivariate normal distribution, so I've got X and Y. Within the bivariate normal distribution, thinking about the conditional distribution of X, conditional distribution of Y, marginal distribution of X, and marginal distribution of Y. People remember sort of this graph, right? So if we go through in this, for any value of Y, or for any value of Y, I slice that, everybody for that value of Y, distribution of X is normal, right? If I look at it the other way, for any value of X, my distribution of Y, it all looks normal. So if I've got lots and lots of data, right? If I have 10,000 people, right? I take everybody who's got a value of 1 on X and look at the distribution of Y for everybody who has a value of 1, it's normal. If I look at everybody who has a value of 5, it's normal, so on and so forth. The same thing the other way, right? What we have when we get into multivariate analyses is we take that bivariate normal, that concept of bivariate normal distribution, or X and Y, throw up X and Y. Show me X and Y. There we go. There we go, and then stick out, now we got 3 axes, now we got 3-dimensional space, right? And so we can see sort of 3-dimensional space here. Now all of a sudden, so this is with 2 variables. Now if we start to get 3 variables, 4 variables, 5 variables, now we're in multi-dimensional space and it's hard to wrap our heads around, right? And so multivariate normality is very, very difficult to test directly or to think about. And so what we need to start doing is starting to make some inferences about multivariate normality based on bivariate distributions and univariate normality and things. Generally, a lot of our univariate multivariate tests have been assumed to be robust, but that's starting to become increasingly in question, particularly when we have other ways of analyzing things with advances in statistics and different ways. So we won't necessarily have to, well, I hope it's robust and we should move forward, but we want to go through and test it. If it's not, then think about if there's another option in terms of analysis. Okay? So you always want to be testing this stuff. All right, distributional assumptions. For our multivariate assumptions of multivariate normality, going to be different in grouped versus ungrouped data. For our ungrouped data, we are going to assume multivariate normality if each variable follows a normal distribution and bivariate relations are linear and heteroscedastic. Okay? For my ungrouped data, for my regressions and things along those lines, if all of my individual variables have a semi-reasonable normal distribution and all bivariate combinations of my variables are not nonlinear in nature and homoscedastic, we'll talk about what that is. Basically, you're saying the same sort of pattern of variance across the whole set. If I have, basically, I want to see if this is my regression line, my individual predictors, look something like that. It's a heteroscedastic relation, right? But if I have something that looks like this, that's not, right? What I'm saying is as X increases, variance in my Y increases. There I have violation of homoscedasticity or violation of, it's basically homogeneity variance or test, right? So as long as my, each one of my variables follows a normal distribution and they're linear and heteroscedastic or homoscedastic, I'm going to assume that I've sort of generally met criteria for multivariate normality. Okay? For my group variables, or for my group data and my grouped analyses, again, we're worrying about sampling distribution of the mean. Okay? Chris, what's my sampling distribution of the mean? Normal? Yeah, and how is my sampling distribution different than my observed distribution? Someone help them out?
Is it a line?
Well, not quite. sample use, yeah, tomorrow you got it.
It's of the, like, means of the population.
Yeah, right.
not
So
parts.
I can have a distribution that's quite non-normal, right? Something like, again, substance use, right? So binge drinking episodes. That's not normal. And if I assess it, it's probably not going to be normal, right? As long as I have a reasonably sized sample, the distribution of the sample means it's still going to be normal, right? So with our grouped-based analyses, we're less concerned about the observed data, so long as our sample sizes are relatively large and we don't have really weird, strange, obscene outliers, which doesn't happen as much in our field as it does in other fields where, like if I'm looking at income and I accidentally captured Mike Bloomberg in the thing, like that's an intense. I did this, so they were talking about like in the Democratic primary, he had spent like $4 million on advertising, but the guy's worth like $50 billion. Like, how did they try to? If I had $100, it's like I spent 80 cents on something. that's so proportionally what that's going on. Just kind of blew my mind about it. So there's that guy, so it's a $4 million between friends on a couple month trip on stuff. But in general, in psychological science, we just don't have people who can be those types of outliers in our stuff. But we still want to go through, take a look, and again, for our group-based analyses, if we've got things that are our cell sizes are reasonably large, it makes us pretty robust to those types of concerns. Okay. Skew, positive skew, dragging the skew higher or the tail higher. Negative skew, things pointing lower. Problem with skewed data is that we're concerned that the mean's no longer our best measure of central tendency, right? Particularly if that skew starts to be pretty extreme, starts dragging that mean value out away from the center of the distribution, right? What we see with our skew distributions, our mean is going to be dragged out to the tail, our mode is going to be there at the hump, and our median is there somewhere in the middle, right? So what's our best measure of central tendency for a skew distribution? Median, right? So thinking about that. Our kurtosis, this is our fourth population moment. Positive kurtosis, or leptokurtic, this is a peaked distribution. Something got a really thin top, kind of flat tails. Negative kurtosis, this is platykurtic, flat center, heavy tails, kind of dome looking, right? We're concerned that our kurtotic distributions, both positive and negative, tend to underestimate the population variance, okay? You can start to impact quality of variance tests, standard error types of things, so we want to go through and take a look at that, okay? Now we know, and Ignacio, this is something you had brought up at some point, there are indices, we do have indices of skew and kurtosis that are available, right? I can test to see whether or not I have significant skew, okay? Nick, I would argue that those are rarely useful. Why am I arguing that testing for significant skew or kurtosis is rarely useful?
Because it depends on what kind of design that you have that is your N increases, it becomes negligible if you have a large skew, and it's
More likely than not, like, it's bound to happen via getting a wider range of people.
Okay, so I start to get people, start dragging people out to the tails. That's important. What else?
There's a lot of things that we're looking for at these streams. So, for example, like if we're looking at levels of ecology, there are fewer people that are likely streaming on some sort of restricted measure, so they're going to generate positive skew.
Okay, so we might not be terribly concerned about whether or not it's skewed, or we might expect our data to be skewed. Why might I not care whether or not I have statistically significant skew?
I mean, if you have enough people, it's going to be significant, but that doesn't mean it's a problem just
Yeah.
because you have that.
Exactly. The assumption of our data is not that we have zero skew. Okay. The assumption is that it's sort of reasonably meeting things, and if I start to have lots and lots of people in my sample, which is good, right? Then all of a sudden, my tests of significance, statistical significance, start to get very, very, very powerful, right? And again, if I've got 500 people, any small deviation from zero is going to give me a significant skew. It doesn't necessarily mean I have anything wrong with my data, right? And so remember that a significance test is just testing whether or not we have evidence against the null hypothesis that something is 0. But if something is 0 is not really relevant to what we're doing, we probably don't need to be too concerned about it, right? So again, using skew and kurtosis guidelines of about 2, right? We might say, so, and we don't want to say that anything that has skew and kurtosis values less than 2 is normal, because it's not. I mean, if you look at it, it's clearly not normal. But we might say values of skew and kurtosis were acceptable, values of skew and kurtosis failed to provide evidence for problematic deviations from normality, right? So just using some of this type of stuff. Now, if we start to get into large samples, we get a skew less than 2, kurtosis of 8. I mean, so that's some Klein stuff that's probably stretching it. Like, I wouldn't say that that's approximating normality, right? But given sufficient sample sizes, I might say that these data did provide evidence of deviations from normality, but those are not reaching the level of problematic. Batching of Dell, talk about positive kurtosis at, so it's starting to be negligible at 100 people, right? So that's peak at distributions. Negative kurtosis, that's kind of more domed. By the time I hit up to 200 people, starting to be less concerned about things. So definitely what we want to do is using our histograms to go through and take a look at what these data look like. So not just relying on indices of skew and kurtosis, and never in this class will I ever ask you to interpret whether or not skew values or kurtosis values are different than 0. What we're going to do is graphically look at sort of the distributions and then try and make a judgment on whether or not this is problematic or not. All right, that's it. We'll do that. So we'll pick back up here when we get back. We'll probably, hopefully we'll get through, maybe, I don't know, it's going to be a stretch, but hope to maybe get through screening next time before sending everybody off to, next week before sending everybody off to spring break. People working together in groups, that's going well. Let me know if you're running any questions. Problem set 2 will be due on Friday at noon, so just make sure that you've got that, your time planned, so you get that all into me by then. I think that's it.
This Friday.